Today we're going to look at a connection between simplex graphs and the graph Cartesian product. Does anything interesting happen if we take the Cartesian product of two simplex graphs? For example, let's take the Cartesian product of the simplex graph of the graph with one vertex with the simplex graph of the complete graph on two vertices. Our result is isomorphic to Q sub 3, the three-dimensional hypercube. What's really interesting about this is that Q sub 3 is itself a simplex graph. Specifically, it's the simplex graph of the complete graph on three vertices. Already, you can start thinking about when the product of two simplex graphs produces a simplex graph, and whether or not this is always the case. As another example, let's take the Cartesian product of the simplex graph of a two-vertex path graph with the simplex graph of a three-vertex path graph. It turns out that this result is itself a simplex graph. It's the simplex graph of the graph shown here. You can spot a pattern already if you look closely. What relationship does the original graph of the product have to the original graphs of the factors? For one thing, the graph on the right is the join of the two-vertex path graph with the three-vertex path graph. In our previous example, K sub 3 is the join of K sub 2 and K sub 1. So now that we have a hypothesis, let's investigate whether this relationship always holds. First, think about the vertex set of the simplex graph of a join of graphs G and H, and the vertex set of a Cartesian product of G and H's simplex graphs. It turns out that we can build a one-to-one correspondence between the set of cliques in a graph join and the Cartesian product of the cliques of the input graphs of the join. In other words, the cliques in the join of G and H correspond nicely to an ordered pair of a clique in G and a clique in H. By the adjacency rules of a graph join, any clique in a join of G and H must be the union of a clique in G with a clique in H. Also, every union of a clique in G with a clique in H must be a clique in the join. So we can define a bijection that will send any clique C in G join H to the element AB of the Cartesian product of the set of cliques of G and of H, where the clique C is the union of clique A with clique B. This is promising because in order to show that for all G and H, the Cartesian product of K of G and K of H is isomorphic to K of G join H, we only have to show that this correspondence preserves adjacency, which would make it a graph isomorphism. Let's consider an arbitrary pair of adjacent vertices C sub 1 and C sub 2 in the simplex graph of the join of G and H. Without loss of generality, suppose that C sub 1 is the larger clique of the two. Note that from this point forward, we'll say that two cliques are adjacent if their corresponding vertices in the simplex graph are adjacent. We know that both C sub 1 and C sub 2 are the union of a pair of cliques from G and H. So let's denote the cliques in G by A sub 1 and A sub 2, and the cliques in H by B sub 1 and B sub 2. This means that the image of C sub 1 under F is A sub 1 B sub 1, and the image of C sub 2 under F is A sub 2 B sub 2. By the fact that C sub 1 and C sub 2 are adjacent, C sub 1 must differ from C sub 2 in the presence of a single vertex V. This means that C sub 1 is the union of C sub 2 and the set containing V. Since V was a vertex in G join H, it either came from G or from H. If V was a vertex from G, then in G, vertex V must be adjacent to all vertices in clique A sub 2, meaning the union of clique A sub 2 with V is a clique in G, and is equal to clique A sub 1, which is the set of vertices in C sub 1 that came from graph G. Also, notice that B sub 1 must equal B sub 2, as if the vertex V that's present in C sub 1 but not in C sub 2 was from graph G, then the set of vertices in graph H in both cliques must be the same. What does this mean for the pair of the images of C sub 1 and C sub 2 under our mapping F? It means that the right entries are equal and the left entries are clicks that differ by a single vertex in G, meaning that they would be adjacent in the Cartesian product of the two simplex graphs. Now let's take a step back and think about the case that vertex V came from graph H. In that case, in graph H, vertex V must be adjacent to all vertices in clique B sub 2, meaning B sub 2 plus V is a clique in H and is equal to clique B sub 1. Also, it implies that clique A sub 1 equals clique A sub 2. What does this mean for our images under F? It means that the left entries are equal and the right entries are adjacent vertices in K of H. This means that our images are adjacent in the Cartesian product of K of G and K of H. Altogether, we can now say that if two cliques are adjacent in the simplex graph of the join of G and H, then their images are adjacent in the Cartesian product of the simplex graphs of G and H. What about the other direction? If the images of C sub 1 and C sub 2 are adjacent in the product of the simplex graphs, is it true that C sub 1 and C sub 2 are adjacent in the simplex graph of the join? First, if these two vertices are adjacent in the product, it means that either B sub 1 equals B sub 2 and A sub 1 and A sub 2 are adjacent in K of G, or A sub 1 equals A sub 2 and B sub 1 and B sub 2 are adjacent in K of H. Regardless, this means that C sub 1 and C sub 2 differ by the presence of a single vertex, so they must be adjacent in K of G join H. We're all done. F is an isomorphism. Isn't it neat that the Cartesian product of two simplex graphs is always a simplex graph? To finish this video, I'd like to show you why the tensor product of two simplex graphs is not a simplex graph in all but one case. First, remember that a simplex graph is always connected and bipartite. So in order for the tensor product to produce a simplex graph from simplex graph inputs, it should preserve the qualities of being bipartite and being connected. However, if we think about the tensor product of bipartite factor graphs G and H, each with more than one vertex, will not be connected. Because if we have parts A sub 1 and B sub 1 in G, and A sub 2 and B sub 2 in H, and we select a pair of vertices from A sub 1 and A sub 2 to be our first tensor product vertex, and a pair of vertices from A sub 1 and B sub 2 as our second tensor product vertex, then there can be no path between those vertices in the tensor product. That's because we'd need to take an odd number of steps to make the right entries equal, but an even number of steps to make the left entries equal, due to the adjacency rules of a tensor product. So, besides the trivial case where both simplex graphs have only a single vertex, which is the simplex graph of a graph with no vertices, the tensor product of simplex graphs is never a simplex graph. As an exercise, I encourage you to think about other graph products and whether those products of simplex graphs will always be simplex graphs, and if not, whether they fail always or only sometimes. Additionally, it's interesting to think about whether or when products of non-simplex graphs can produce a simplex graph. That's it for this video. Thanks for watching. If you enjoyed this video, please subscribe and click the like button. Have a great day.